Okay, so the first thing that I owe you from yesterday's lecture 3 precise definitions, which I'll just put on the blackboard so that if you want to think further about the groups that I have defined yesterday, you can do it with a clear definition on the blackboard. Yeah. So these are the following. So recall from yesterday the Hamiltonian, which I will denote h mu nu, and which had this shape. Yeah. Where here I had the boundary of v, boundary of w, and then slope mu, and then going up to some delta, and I will not include the delta because it depended on this slope, essentially. It was small enough and depending on this slope. Yeah. And so I will write what this relative symplectic homology group is. Yeah. And I had argued that you want to take into account for this relative homology groups these guys, right? Orbits here, and orbits here. So it was 3, 4, and 5. Yeah. If you look back in your notes, that was the idea. Take into account topology of this part and then dynamics on both the concave and the convex boundary. Yeah. So the way you can do that is by taking this Floer homology group for this Hamiltonian h mu nu and pick action truncated up to some finite value. Yeah? So you're going to let the slope mu go to infinity, so you have to think of this as going down. This should go up and have, so because this goes up, it's going to be a direct limit. This goes down, it's going to be an inverse limit. Yeah? So you take first inverse limit along mu, direct limit along nu, and then direct limit over A. Yeah? And this is going to do the job. It's going to see what you wish. Yeah? So for what I had denoted like positive part, yeah, I want to exclude the 4. I want something like 3 and 5, and same procedure, right? So it's going to be the same object, except that I exclude the 4 which had action 0. So I'll just truncate in some action window epsilon A. And again, h mu nu, yeah? And inverse limit over mu, direct limit over nu, and direct limit over A. Yeah? And epsilon here has to be small. Yeah? And in our case, smaller than the minimal period of a closed characteristic on the boundary of V or on the boundary of W. Yeah. And then also so these are the 2 definitions that I owed you precisely, yeah, because yesterday it was a little bit vague in the last argument. And finally, I want to also put on the blackboard a precise definition of what SH star plus of some Liouville domain, or W, is. So recall that to define symplectic homology, we took Hamiltonians like that. And for the plus part, I want to exclude the guys here. So I have some orbits here, and I just want to take these into account. I want to exclude those. And those have small action. So again, this is going, if this was the Hamiltonian HA, say, A is not, yeah, let me call it H mu now. Yeah. So you take Floer homology of this Hamiltonian H mu, and you just truncate it below, yeah, above some epsilon small, and you take a direct limit over mu. And it's going to do the job for you. And these are the groups that appear. Yeah. So so again, this is in order for you to have a very precise definition if you want to think these things over further. Yeah. But today I want to change a little bit direction, yeah, and in the following sense. So I want to introduce a new question. So, and before introducing a new question, which is going to motivate my construction, I want to give a definition. Yeah. So recall the notion of contact manifold. Yeah, contact manifold. Yeah. And then a submanifold L of dimension n-1 in M is Lagrangian, yeah, if it's everywhere tangent to psi. Yeah, and remark just like given the contact manifold M, you can associate to it its symplectization, yeah, which I have once you choose a contact form, you can write it as a 0 infinity cross M, right? So that's the symplectization. And then, of course, inside here, you have 0 infinity cross L. Yeah? And L is Lagrangian if and only if its symplectization is Lagrangian. Right? So then L is Lagrangian. If and only if infinity cross L is Lagrangian. Right? So just as I said that contact manifolds are odd-dimensional counterparts of symplectic manifolds, the counterparts of Lagrangian submanifolds are Lagrangian submanifolds inside here. Yeah? So the following question is called the Arnold conjecture, chord conjecture. So that means that Arnold conjectures that the answer to the question is yes in certain cases. And the question is the following. Given some Lagrangian in a contact manifold, right, and a contact form, alpha, does there exist a Reb chord with endpoints on L? Yeah. So what's a Reb chord? It's a curve defined on some interval such that its it's an integral curve for the Reb vector field. And such that gamma of 0 and gamma of t belong to L. Yeah? So you have to, so again, there's this in the in the closed case, if you wish, there's this Arnold conjecture that Mihai stated, right? Asking for fixed period orbit. Yeah. And then there's also the Lagrangian fixed period orbits, and then there's the Lagrangian analog, the Lagrangian version, which asks for intersection points of L and phi 1 of L. Right? So, as I tried to convince you, in the open case, we're looking via the Weinstein conjecture to fixed energy orbits, and I just put it at the singular. We're in general looking for one, and proving more is a very difficult task, as some people in this room know very well. And so now the analog, so this would be analog, an analog to the Arnold conjecture, if you wish, right? By trading fixed period to fixed energy level, right? So the analog to the Lagrangian version would be to look for a Reb chord. Yeah? So that would be a Arnold Reb chord. Chord conjecture. Yeah. So we're looking for a chord, yeah, on fixed energy level. So what I want to prove is that what I will prove today is that the Reb, the chord conjecture, holds true, yeah, in certain setups, yeah, and that there is a Lagrangian version of symplectic homology that plays a role in that. Okay, so today we define a Lagrangian version of symplectic homology, yeah, which is going to be useful to prove, in particular, the chord conjecture in many relevant situations. Yeah. So now I have in my first lecture I have used the symplectization as a motivation to look at symplectic manifolds which are open, right? And convexity, so the fact that that the Liouville vector field was pointing outwards along the boundary definitely played a role in the definition of our invariants, right? So it was this kind of, the fact that the Liouville vector field was pointing outwards is a manifestation of convexity and was enabled us to prove the maximum principle and hence to define the objects, right? So if we want to think about a Lagrangian version of symplectic homology, right, what we should think of are Lagrangians, yeah, that if this is, say, our Liouville domain, and here it's the symplectization part, we should think of Lagrangians that enter the symplectization part in a cylindrical way, right? So we should think of Lagrangians that have this, yeah, something like that. They do whatever. For example, yeah? So some Lagrangian submanifold, yeah, that enters the symplectization part cylindrically. And I just told you that if it enters the symplectization part cylindrically, so this, it means that the submanifold along which it's going to intersect the boundary is going to be Legendrian. Yeah? So we consider Lagrangian submanifolds L hat in W hat, where this is the completion of a Liouville domain. Right? And such that on L hat intersected 1 infinity cross boundary is 1 infinity cross L, yeah, and then necessarily L is Legendrian. Yeah? So an alternative point of view, if you want to take it from the point of view of the Arnold-Core conjecture, which is formulated for contact manifolds, not for symplectic manifolds, is to say the following. Think in this picture of the boundary as the primary object which interests you. Yeah? So there's a contact manifold. This contact manifold is fillable, right? It has this filling, which is W itself. And we consider inside this contact manifold Legendrian submanifold, which is fillable too. But now fillable means it has a Lagrangian filling, right? So this is a different point of view, right? Point of view, we consider pairs M, L, right, such that M is exact fillable, right? So i.e. M is the boundary, contact boundary for Liouville domain, and L is fillable too. And, well, let me write exact fillable, meaning that L is the boundary of some Lagrangian, yeah, with L contained in W, Lagrangian, yeah, which is exact, yeah, and which intersects the boundary transversely. Yeah. So of course now, as I have said in my first lecture, this exactness assumption is there just to make things easier. So in particular, it prevents bubbling, right, of holomorphic spheres. And if we assume the Lagrangian to be exact, then it prevents bubbling of holomorphic disks. So Floer homology is defined, right? We do not have to worry about those things. But of course, there are setups in which, more general setups that you may wish to consider, and in which you can assume that the filling is monotone or whatever, yeah, depending on your taste and courage. But anyway, this is the setup that I wish to consider now. So now there's a very simple way to there's a very simple way to exhibit Reb chords, right, inside a Floer type complex. Yeah? And how do you do that? So as a matter of fact, I think I can write a definition now. Yeah? So everything is as before, and you set SH of L, yeah, to be the direct limit over A, Floer homology of L intersected phi flows where little phi 1 HA of L. And this HA belonged, as before, to HA. So let's see what I have done here. Let me give this gadget a name. Let me call it so you can call it as you wish, but people usually call it a wrapped Floer homology. Yeah. And it's because, so that's the terminology of Seidel and Smith, and I guess Fukaya. Yeah, I think it appears, the definition, for the first time in one of their papers. But you could also wish to call it Lagrangian, symplectic homology, or whatever. The important thing is what it is. Yeah? So, nevertheless, this name gives you some intuition. So what has happened here? When I do, maybe I'll write this, transverse intersection. So, I have this Hamiltonian HA, boundary of W, yeah, with some maximal slope here. Okay? So if you imagine that inside the manifold it's a C2 small function, C2 small Morse function, and assume that here, so if HA is on the W, C2 small, sorry, I'm writing twice the same thing, but I think it's Morse function, and on 1 infinity cross boundary, HA of Rx is, and may even TRX is equal to some H of R, yeah, with H of R equals to some AR plus B for R large, yeah. What has happened? So we know that the Hamiltonian vector field is proportional to the Reb vector field by the slope, right? So it means that at time 1, yeah, at time 1, if I try to draw maybe this would be the boundary of W, right? So phi 1 of HA here, right, will make me move in the direction of, actually the opposite direction of the flow, if I parameterize by the Reb vector field by some time equal to h prime at the corresponding level, right? So if this is the level r, right, at r equals 1, say, I move by along the Reb vector field minus the Reb vector field by a time equal to h prime of 1. At level 2, I go along the minus the Reb vector field by a time which is going to be h prime of 2, which is going to be strictly larger because this thing h is convex and h convex, right? So I move here like that, then like this, and then as I go up, I start, I mean, in this picture with a cylinder, right? You have to imagine that I'm moving, whoops, maybe this is h prime of 3, an even larger time, that's for r equals 3, and so on, right? So it means that inside the manifold, I just have a very tiny perturbation, which is going to change my Lagrangian tinily and make it intersect itself, right? So the if I do again the same picture, say, and the Lagrangian is, for example, this one, yeah? So what happens is that in here, my Lagrangian is changed just a little bit. This is the boundary. So it's going to do something like maybe like this, like this. Maybe it's going to intersect again once. Very tiny, right? Yeah. And then out of a sudden, as I enter this region, what are going to be, so I'm going to be translated by exactly the same thing, right, here. And then the Lagrangian, by the flow, is going to start being displaced, right? So, yeah, and it's going to be start being very, very displaced, right? Maybe like this. Yeah, like this. And actually, here it's going to be displaced by some fixed quantity. And I'm going to see as intersection points exactly Reb chords. Say like this, right? So, sorry, it has to stop at some point. I'm sorry. So what has to happen? So at some point I have to stop displacing and say I reach here. Yeah. That's time 1. And what I have drawn here is phi 1 HA of L. Right? So I'm moving at every level R by some quantity, right? Yeah? This quantity varies in the part where the Hamiltonian varies. Where the Hamiltonian has constant slope, I move everything by some quantity equal to the slope, A, right? If that quantity is not the period, is not the length of a Reb chord, it's good. I do not have intersection points at infinity, right? So, and here, A is different from period of Reb chord. Yeah? So if A is different from the period of the Reb chord, I don't have intersection points at infinity, and I will see in this complex something which is related to the topology of L, related in the interior of W, where I have made a tiny deformation, and then as generators, all the Reb chords up to period A. Right? So it's good. It's exactly what we want. It's a precisely analogous picture to what happens in symplectic homology with periodic orbits, but now I have incorporated in here Reb chords. Right? Good. So, I mean, the generators in Fc star of L, phi 1 HA of L, yeah, there are two types of generators. Small intersection points of L with itself, with phi 1 HA of L, yeah, that's in W, and then Reb chords of length at most A. And as I let A go to infinity, everything's fine. I will have taken into account the whole story. Yeah? So, of course, there's maybe one thing to prove, namely that this maximum principle, yeah, that if you are looking at strips, yeah, you cannot have a maximum. Yeah, I mean, they all stay in a compact set. Yeah. So yes. Yes.
To get a non-degenerator orbit in the Floer sense,
indeed.
You have two generators.
Correct.
And you don't have this trouble here.
No. No. So for that's a fantastic observation, and thank you for it. Thank you for this one. If the contact form is generic, so what kind of Reb chords could you have? This is the Lagrangian L, right? And you could have Reb chords which come back on the Lagrangian on some different point than the one they have started with, yeah? But if by bad luck there's a periodic orbit which intersects the Lagrangian, right? That is going to give rise to infinitely many generators, right? It could be that you have a periodic orbit, right? Periodic orbit. But for a generic choice of the contact form, periodic orbits are not going to intersect the Lagrangian. So for generic choice of the contact form, these guys are automatically non-degenerate, and moreover, distinct generators correspond to distinct Reb chords. Yeah? So this is going to be useful right away, yeah? Because we're going to be able to infer not only the existence of one Reb chord, but multiplicity result for generic choice of contact form. Okay, good. So to be proved here, maximum principle, yeah, which I will not do because it would essentially repeat the computation, and then there's a tiny argument. So on the boundary, one can use a reflection principle. Use reflection principle. So I will actually prove something, hopefully something more powerful towards the end of the lecture. I want to write what the formal properties of this object are. They are absolutely, actually it turns out fine because I'm going to write them on the same blackboard where I wrote those for symplectic homology. Right, so properties. Yeah. So the first one for symplectic homology was that it is a ring with unit. Yeah? So this guy is also a ring with unit. Ring with unit. And I have not insisted, so for symplectic homology, the ring is commutative. For this guy, it's non-commutative. Non-commutative in general. Yeah, SH star is commutative ring. Yeah. So that's yeah. I'll talk about the ring structure. Yeah. There's a map. There's a map from the relative homology. As a matter of fact, so this is something that I'm not. I will not write the degree because I'm not sure about it. It will not be relevant for our purposes, but I'm not sure about the degree. Let me not write. I'll just write this, like homology goes, this is the same as cohomology in complementary degree, and there's this map to symplectic, to wrapped Floer homology. I'll not write the degree, but anyway, the unit here goes to the unit there. Yeah? And this is a map of rings with unit. Map of rings. With unit. What other properties did I have? A commutative diagram, right? I don't know. Maybe I'll just erase here. Commutative diagram. So 3, functoriality. Yeah, if you have V, an inclusion of Liouville domains, right? And then you have here LV, which is contained in L, yeah, as before. Then you have such a map, right, from L, the bigger one, to LV. Yeah, and we can even right, this is like this, L, and this is like this, LV, and you can actually complete it to some relative homology group. It's a completely analogous story. Yeah, and so on. Yeah. But now, as a matter of fact, right, so I will so this thing was proved by Ritter. So Ritter has a paper in which he treats these things in parallel. It's called TQFT structure on symplectic homology. Yeah. So there he also defines this and studies some of the properties, and in particular he proves the ring structure. And the property that's going to be very, very interesting for us is going to be the following. So this guy is a ring with unit. Symplectic homology is a ring with unit. And this one is a module over this one. Is module over SHW. So this property is going to be the one that, so this is proved again by Ritter in his paper, and he said it had been observed by other people before. So this property will be most useful in order to show that the Arnold core conjecture holds. Yeah? So here's the theorem. Yeah? So assume symplectic homology vanishes. Yeah? Then, right, let L in the boundary be an exact fillable Lagrangian, and denote by L its filling, the filling. Then the Arnold chord conjecture holds for this Lagrangian, meaning there is, for every choice of contact form, there exists a Reb chord with endpoints on L, and this Reb chord may be closed. Yeah, we know, we don't know. Yeah? And if alpha is a generic contact form, then the number of Reb chords, then I would say, then all chords are simple, and the number of Reb chords is bounded below by half the rank of the homology of L. Yeah, I don't know why. I mean, by writing the statement this way, I don't need to denote the filling by anything in the statement. Okay. So, how is this proved? Yeah, this is a 3-line proof using the module structure. Yeah. So what does it mean? Module structure means that I have an operation of this yeah? That's what it means. You're going to say this guy is 0. What are you writing on the blackboard? That's what it is. Yeah? Let's pretend we do not know that it's 0. This operation is there. Yeah? So then let's pick x in the reft Floer homology of L. So the module structure over a ring with unit among its axioms means that the unit acts trivially. So 1 times x is x. Yeah? But 1 is equal to 0, so 1 times x is 0 times x. And 0 times x definitely is 0. Yeah? So that means that the wrapped Floer homology vanishes too. Yeah? But that's very interesting, because we know that there's this on the other hand, right? On the other hand, so we have this map, right? cohomology of L going to the symplectic homology of L, right? Of course, I can even insert this map into a long exact sequence where this thing, which I will write like this, I'll write a plus version. Same story as before. Plus version means what we see in this region up to here. That's SH plus of L. We truncate in positive values of the action. Yeah? So if this thing is 0, it means these guys are isomorphic. But this guy here is going to be generated by the Reb chords. So it means that the number of Reb chords, first of all, it means that this guy is if this is 0, it means something kills the homology of L. So there is at least one Reb chord, right? So this implies, first thing, since this map, C star, is not an isomorphism, there exists at least one Reb chord. One Reb chord. Yeah? Second, for generic alpha, Reb chords are simple, meaning they're not periodic, and their number is bigger than the rank of this part, right? So their number, the number of Reb chords, is bigger than the rank of the positive part of wrapped Floer homology, and this in turn is equal to the rank of the cohomology of L. Yeah. So I could have phrased the conclusion of the theorem in terms of the rank of the homology or cohomology of the filling. But if I want to phrase it in terms of something that depends only on the Lagrangian, it's enough to pass from this to the Lagrangian via the long exact sequence of the pair, right? So you have the pair H, L, L, and then H, L, and then H of L, like this, right? That's a long exact sequence. And the rank, these two ranks are equal, yeah? This and this have equal rank. These two have equal rank, yeah? And therefore, these two have equal rank, and hence the rank of the cohomology of twice the rank of the cohomology of L is I'm getting I want to say that this is bigger than the rank of the cohomology of this. Yeah? Right. So indeed, we don't think about about the Euler characteristic of this thing, right? That the alternate sum of the ranks is equal to 0 for a long exact sequence. We just look at this point in the long exact sequence, and because of exactness here, so the kernel of this, so the rank of this guy is bigger than the image of this map, right? On the other hand, the image of this map is going to have rank equal to this guy minus the kernel, but the kernel is the image of this map. So this plus this is bigger than than this. Okay. And this proves that that the rank, the bound that we have here, number of Reb chords is bigger than the rank of the cohomology of the filling, and that's bigger than half the rank of the cohomology of L. So, of course, you have many examples. Now, this finishes the proof, yeah? And for example, if you take if you take the standard Lagrangian unknot, yeah, where is it? In S2n minus 1 with the standard contact structure, right? You take this thing, right? It's going to satisfy, but of course you can choose any contact form there. So that's Rn intersected S2n minus 1. Yeah, that's L. And it is, of course, fillable, and even exact fillable by this guy. Yeah? The rank of its homology, since it's a sphere, so that's a sphere Sn minus 1, is going to be 2, so you get at least 1. Yeah? Well, similarly, in the boundary of a subcritical Stein, subcritical Stein manifold. As a matter of fact, you have many examples of Lagrangian spheres which are exact fillable, yeah, by thinking of, so that's also okay, yeah. So I also mentioned Stein manifolds, yeah, Stein manifolds with vanishing symplectic homology, vanishing SH. Yeah. So those Stein manifolds are actually total spaces of Lefschetz fibrations, and for each critical point of index n of the Lefschetz vibration, there's something that's called the Lefschetz thimble. And the Lefschetz thimble is a disk that is going to intersect the boundary along a sphere, right? And disks are, of course, exact. Yeah. So these Lefschetz thimbles, boundaries of Lefschetz thimbles, L boundary of Lefschetz thimbles. Yeah. And then you can maybe let me recall the following computation. So that's proved by Alberto with Matthias Schwarz. Symplectic homology of the cotangent fiber maybe let me choose another letter, D star Q, some Q. Yeah? So the cotangent fiber is such a Lagrangian that intersects the zero section Q along a Lagrangian, right? So symplectic homology of this guy is the homology of the base loop space. Yeah. That's Abundandolo Schwarz. And actually the product that I'm going to talk about right now is the Pontryagin product here. And the Pontryagin product is very non-commutative. You take two cycles in the base loop space, you make the product by concatenating them at the base point. All right, so yeah. So let's talk about the product and about the module structure. So I think it kind of fit very well that Mihai talked about Floer homology both in the absolute and the Lagrangian setting, right? So he treated them in parallel, and the same thing happens for symplectic homology, right? There's a natural class of Lagrangian submanifolds for which you can define an analog thing, and it has relations to the analog conjecture, right? And then for cotangent bundles or cotangent fibers, the computation that Alberto explained is kind of fundamental. Yeah. So, product structures. So, product structures are defined how should I? No, I want to do something else. Trying to be very. So, recall that the differential for symplectic homology is defined using cylinders. Yeah? You look at cylinders which connect, Floer cylinders, which connect to one periodic orbit. Yeah? Now, for the Lagrangian version, wrapped Floer homology, the differential is defined by counting strips. Yeah? For Morse homology, the differential is defined by counting gradient lines. Negative gradient lines. So now what about the product? I claim that the product for Morse homology, which should recover the cap product, right, in homology, is defined by counting such objects. What does this mean? These gradient lines were actually, in the definition of the differential, you have to think of each critical point as, if you think of cellular homology, as representing the simplex, or the cell, defined by its unstable manifold, right? When you define the differential by such isolated gradient lines, you're actually looking at an unstable manifold and look at its boundary and see which cells of one dimension lower it's going to touch and how many times and with what sign, right? So you're decomposing the boundary of a cell according to other cells of one dimension lower. This is the differential for Morse homology. So now let's think about the intersection product. I have two cycles, right? They're going to intersect and represent some other cycle, right? So now if these two cycles are some combination of cells, it means that I have to intersect each two cells. It's going to give something and decompose the result according to the cells of the corresponding dimension, right? That's exactly what happens here. I'm intersecting W of some point X, unstable manifold of some point Y, right? They are going to intersect. And if I want to express that as a linear combination of cells, I have to let it flow and see where it gets hung up. So I'm going to flow with some stable manifold of a point Z. For three different functions in order to achieve transversality. So three different functions. So I have given you a heuristic interpretation, explanation of why counting such objects would define the product. Yeah? So now, if you agree that this guy in Floer homology gets thickened to a cylinder, such a thing is going to get thickened to a pair of pants. Right? These are the entries. X, Y, this is the exit. And in the Lagrangian version, a segment gets thickened to a strip. And this guy is going to get thickened to a triangle. I'll draw the triangle this way. Minus infinity, plus infinity. So what does, by the way, just like a pair of pants conformally from the point of view of complex geometry is the same as a sphere with 3 points taken away, this triangle is the same as the disk with 3 points on the boundary taken away. Yeah? So now commutativity of the product in the periodic setting comes from the fact that there's no natural order on the points. Say these are the entries and this is the exit. There's no natural order between these two. You can interchange them. But on a disk, if these are the entries and this is the exit, of course there is a natural order, because the disk is a Riemann surface. It comes with an orientation, and the boundary comes with a natural orientation. So these guys are ordered, and it's because of that that the product is going to come out to be non-commutative. Okay. So now arises the issue of course, what am I counting here? I have to write an equation defined on this Riemann surface, right? So I will take the point of view, the very elegant point of view that's developed by Seidel in his paper Biased View. On symplectic homology, cohomology for him. So he takes the point of view, the following point of view method to define a Cauchy-Riemann equation. I'll write a Floer type equation on a punctured Riemann surface. So you take your Riemann surface, S punctured, Riemann surface. Yeah? So assume for the time being that it has no boundary. Yeah? No boundary, which would correspond to this thing, right? So no boundary, now you have to declare what are the negative punctures, what are the positive punctures. What does it mean to declare a puncture to be negative or positive? You have to choose conformal coordinates there, which are modeled either on minus infinity cross S1 in polar, or on 0 infinity cross S1. So choose for each puncture, set polar coordinates modeled either on minus infinity cross S1, that's negative, that you call a negative puncture, or 0 infinity cross S1. That's a positive puncture. Yeah. Yeah. So pick now a one form, beta, right? Such that in the neighborhood of the punctures, near punctures, beta is constant times dt. So here I have coordinates s and t, yeah? And I want this beta to be a constant dt, and the constant depends on the puncture. Right? So it's going to be important. So for maximum end, d beta non-negative. So that's going to be important for the maximum principle. What does it mean, d beta non-negative? D beta is a two-form on the Riemann surface, and you can compare it. It has at every point a coefficient, and you can compare it with the area form, right? The Riemann surface is oriented. So you can look at that coefficient and say whether it's negative or positive. You don't want it to be negative. Yeah? For example, no example yet. Yeah? And this forces, by Stokes, this forces the fact that the sum of a Ci over the positive punctures minus the sum over Cj's over the negative punctures be positive. Right? You integrate by parts and you get that. And as a matter of fact, this is the only obstruction. As soon as you fix constants at the endpoints, at the punctures, which satisfy this relation, you will always be able to find a one form satisfying d beta positive, non-negative, and with a prescribed asymptotic near the puncture. So now fix a Hamiltonian. H. Fix a Hamiltonian. Say in H A for some fixed A. Fixed generic A. Yeah? And then consider, I'll write M. Of course, there's the J in the background. So I will write M of, no, what do I want to write? Consider, right, so fix asymptotes, one periodic orbits, yeah? So gamma minus is going to be a set of periodic orbits, gamma 1 minus, gamma k minus, that's for the negative punctures, and gamma plus is going to be gamma 1 plus up to gamma k, gamma L plus, and that's going to be for the positive punctures. So now I have everything I need. I just have to write the equation. I have asymptotes. I have this, the Hamiltonian. I have this weird beta, yeah, and I'm going to write, consider this moduli space, gamma plus, and then of course it depends on H, J, beta. And that's going to be the U's defined on S with values in W hat, which are asymptotic to gamma plus minus, and that solve the equation du minus xh tensor beta is holomorphic. So I'm writing here the 0, 1 part of this gadget is 0. Yeah? So now, up to now, in whatever we have said, in all these lectures, we were on a cylinder and we had global holomorphic coordinates st. right? On a Riemann surface, this is not the case. You do not have global holomorphic coordinates, right? So if you want to write down an equation, in particular on the sphere, yeah, you have to write it in a more intrinsic form. Yeah? So, example. Actually, no example. Let me write, note, this is in local holomorphic coordinates, in local holomorphic coordinates, S plus IT, of course, I can write beta as some coefficient beta S ds plus beta t dt, yeah? And the equation, yeah, is equivalent to something that will have a very familiar form. So it's going to be dsu minus beta s xh plus j dtu minus beta t xh equals 0. Yeah? So now comes the example. Yeah? If you take beta, the one form, if you take S to be R cross S1, right? And you take beta to be dt, which is well defined, non-negative, it turns out to be really closed, yeah? And the behavior at minus infinity and plus infinity is the same. You see that the equation becomes dsu plus j dtu minus xh is 0. And that's the Floer equation. So now recall that in considering the moduli space of Floer trajectories, we have quotiented out by R, right? Why was that? Well, it was because we had automorphism. If we had a solution, we could shift it, right? So, well, you can, that's a typically what's called an unstable case, right? We have a sphere with 2 points removed. I still have automorphisms there. Yeah? If I have a sphere with at least 3 points removed, there's not going to be any automorphism. Yeah? So maybe here you have to divide by the automorphism group. Yeah? But I will not be. Yes? Yes, yes, absolutely. You can do that. But for the purposes of symplectic homology, the maximum principle would have been violated. You cannot do that with d beta positive. Right? It has to decrease at some point and increase at some other. It's good increasing. Decreasing is bad. Yeah? If you could have done that, it would have meant that the symplectic homology always recovers the singular homology, which is false. But in the compact case, indeed. Yeah? You can just punch in a Floer type equation near the punctures and then in the rest 0. So the second example, if you take R cross S1 and now you want to mimic a homotopy of Hamiltonians, right? You want to mimic the fact that H increases, depends on S, right? So let me say that it depends ideally on S by multiplying it with a function depending on S. So you take beta to be f of S dt, right? And you see that d beta positive amounts to the fact that f prime is positive, and that amounts to an increasing homotopy, which is compatible with what we saw yesterday. Yeah? So in this case, you get dsu plus j dtu minus x f of s h. I mean, f of s here, but I could just plug it into h as well. So that's a continuation equation. And of course, since beta does not depend, does depend on s, there's no automorphisms, and that's what we did for continuation equations in Floer homology. Okay, so to define the product, we're going to take this data and maybe I have to say something else. So here you see I have imposed b to beta to be asymptotic, to be constant times dt. It means that these one-periodic orbits are not just are not one-periodic orbits of the fixed Hamiltonian H, right? This one is a one-periodic orbit for C1 minus times H. This is CK minus times H. This is C1 plus times H and CL plus times H. Yeah? That's how the thing goes. And it's going to, so the count of elements so, is going to define a certain map. So now, in the particular case where S is CP1 minus 3 points, 2 negative, 1 positive, right? So you can define a map that, let me call it phi, from the Floer complex of C1 minus H tensor Floer complex of C2 minus H to the Floer complex of C1 plus H. It's this. That's C1 minus C2 minus H, C1 plus H. And that's encoded in the fact that beta is equal to blah dt and so on. Right? And this is a chain map. Why is it a chain map? Because it is in a, oh, I haven't said what it is. Right? You take gamma 1 minus and gamma 2 minus, and you send them to a sum over gamma 2, gamma 1 plus, such that the dimension of this moduli space, gamma 1 minus, gamma 2 minus, gamma 1 plus, and with the rest thing is 0, so H, J, beta is 0. Count the number of elements in this moduli space. And put as coefficient gamma 1 plus. Right? And this is now this is the unfolded version of that picture. That pair of pens defines product. That's what I mean by pair of pens defines product. I mean, I can look at some equation, I can count the elements in the zero-dimensional moduli space, and that is going to give rise to a map which is a chain map. Right? Chain map. So why is it a chain map? Well, it is as in the case of Floer homology, we look at one-dimensional, the boundary of the one-dimensional moduli space. Yeah. So what am I looking at? I'm looking at a one-dimensional moduli space of such objects. Right? And you pass to the limit, you have uniform C infinity lock convergence, right? So it's going to converge to something that probably will have one different asymptote, which I'm going to draw in, yeah? And the others have to be the same. Yeah? But then if you shift attention very, very close to this guy, right, you're going to see, like in the proof of compactness for Floer homology, a Floer trajectory popping out. That's going to be symptotic to gamma 1 minus. So that's one possible degeneracy. But what does it mean? Here I'm in a moduli space of dimension 1, and I'm converging to something that's going to be dimension 0, and this is going to have index 1. So that's going to be part of the differential, and that's going to be part of this operation. Right? And you do not have to worry, even in the case of arbitrary genus and arbitrary number of punctures Riemann surfaces, because although I have not written it here, with fixed conformal structure, I do not vary that. Of course, for the sphere, this is an empty assumption. But even for arbitrary Riemann surfaces, I fix the conformal structure. Nothing is going to take place like in the Teichmüller space. Nothing, right? What happens is just degenerations of Floer type. So that's one possibility. The other possibility would be that you have this, but then here you end up into a different asymptote, right? And then see a Floer trajectory ending up at gamma 2 minus. And then another possibility, let me separate the pictures here. Yeah? And then yet another possibility is that in which you have loss of compactness at this other end. So it would be this kind of picture. Right? But what you see as boundary, as possible boundary, bubbling is excluded at everything. What you see here is phi composed with differential on this factor, phi composed with differential on this factor, and the differential on this factor composed with phi. So the sum of all those guys is equal to 0, and that's exactly condition of being chain map. So then you have to take care a little bit and make sure that all this thing is compatible with continuation morphisms. So this procedure is compatible with continuation maps. So you pass to the limit over this constant going to infinity, this constant going to infinity, and this. Remember that h was living in some is fixed once and for all. It has a definite slope. So if you let this constant and this constant go into infinity, this one also has to go to infinity, and the slope goes to infinity, and in the end you get this map. And that's the product. Yeah. Direct limit, and this is the product. So what about the unit here? Well, so what's the unit? The unit is a distinguished element in your homology group, right? So the unit is a distinguished element, and if you want to produce a distinguished element, you'd better count things defined on a Riemann surface that has only outputs, and preferably one output, right? Nothing is in. Nothing comes in, something comes out, the element. So the unit is a count of this positive puncture. Yeah? For any Hamiltonian. You look at an equation of the same form defined on the sphere with just one point removed, where you have a Hamiltonian condition at this point, same trick, form beta, right? pass to the limit, that's the unit. It may vanish if the whole thing vanishes. And why is it the unit? Proof that it is a unit, that E is unit. So you have to plug, so E times X has to be X, right? What does it mean, E times X? It means that I take the gadget that defines the product, yeah? That's the product. At one end, I plug in X, which is an orbit. And then the other, I plug in this guy. But this guy is the count of these things. That's E, right? So I have to count concatenations of such pictures. But as Mihai has shown, here, I have two things which are asymptotic to a periodic Hamiltonian orbit, plus infinity, minus infinity, you can glue. The one form is the same, it's dt, it's just usual gluing for Floer homology, except that the domain is a little bit trickier, right? So this is going to produce the same thing as this thing. But of course, this thing is just a cylinder with some equation, right? Which depends on S, on everything. You do not quotient out by anything. But all these things you can interpolate between. The fantastic thing with this class of betas is that it is a convex set. Amazingly, right? It's a convex set. So if I have an equation defined by some beta, of course you can interpolate towards the beta defined by dt, constant dt. And the result is going to be the same. We're just only interested in homology. So this proves that in homology, E times X is X. The fact that you can glue these guys and get the Riemann surface that defines essentially the constant continuation map. So this kind of picture is absolutely, this is why Ritter's paper is called TQFT, because this kind of picture is typical of TQFT, right? You have operations which are essentially defined just by the Riemann surface. Forget about all the auxiliary data, right? Different choice of auxiliary data will give rise to the same operation. It's just the Riemann surface itself that counts, right? So, the outcome of the discussion is that symplectic homology is actually a TQFT, right? So you have operations, TQFT operations, right? So you have, this is the unit, this is the product, unit. You can also have a coproduct. Actually, these, by the gluing relations, are going to determine everything, and this guy does not exist. Co-unit. Non-existent. Why? Because it would mean that you have a positive form with negative integral, right? You can't have just one negative puncture. It would violate the maximum principle. So for reference for this maximum principle in this setup, again, I refer to Ritter for whoever is interested. And I just want to take 5 more minutes in order to show you how the module structure is defined. Because now the way the product structure is defined on the Lagrangian version is clear. Instead of counting pair of pens, you count half pair of pens, right? Triangles, yeah? And you have to impose suitable Lagrangian boundary conditions. It's the exact analog of passing from cylinders to strips. Passing from pair of pens is to half pair of pens, yeah? So for the module structure, yeah? you have to count these guys. No, you want to define such an operation. Yeah? So what does this operation do? Well, now you want one input which is in symplectic homology, namely a periodic orbit. Inputs given by periodic orbits are given by interior punctures. But then inputs given by Reb chords, or Hamiltonian chords, if you wish, are given by punctures on the boundary, right? So we need one interior puncture, one puncture on the boundary as an input, and then we want to spit out one generator of the Lagrangian version. So I'm going to put a puncture on the boundary, which is a positive end, an output, right? If you wish, you can even redraw this business by saying that maybe this is nicer, like this, or like this, yeah? So here I'm asymptotic to some periodic orbit, and here, or even like this, I draw a strip. Yeah, that's gamma 1 minus, gamma 1 minus, gamma 2 minus, gamma 1 plus. Right? And same story. Form beta, which is dt. I choose coordinates. Here they have to be cylinder-like. Here they have to be strip-like, right? And for technical reasons, so same story, right? Choose beta such that d beta is positive or non-negative, and for technical reasons, you want that beta vanishes on the boundary, and d beta is 0 near the boundary of the surface. But that's fine. Beta vanishing on the boundary is no big deal. It's just saying that it's some multiple of dt, right? Typically here, beta, I require it to be some function of s dt, f of s dt. That's what I want from beta, and it's going to grow from C2 minus to C1 plus, right? This f of s. And, well, maybe this is not so good if I'm doing that. Maybe I'm going to erase this. D beta is 0 near the boundary. Probably you can, yeah. Since I don't explain, I can erase it without any problem. But the message is the same. I take one periodic orbit here, some chord, and I spit out a chord, and I get an operation which is defined from the Floer complex of C1 minus H, and then times the Floer complex of L transverse intersection with the flow of time 1 of C1, C2 minus H, and it's going to go into the Floer complex of L intersected time 1 flow of C1 plus H. Yeah? And then you pass to the direct limit, and it's going to be good. And there's this fundamental relation on which rested the application. 1 times x equals x. Yeah? So about 1 times x equals x, the proof is exactly like for the unit there, because the 1 here is actually e, the unit. And so what do you do in order to plug it with x? So you do the same picture here, right? Here comes x, and here you're going to be counting e which is given by this count of planes. Maybe it's not a very good picture. I should put it on the left like this, right? And then here comes E. Yeah. And same thing. This is going to be the same operation as gluing these guys like that. Yeah. But then you can that's gluing. Yeah. And then you can just interpolate beta. And you are going to end up with a continuation equation, which is the identity. And that's going to be identity, continuation equation. And that's it, I think. So this gives you an idea of how these structures are defined. And I think it's, I don't know. Again, for those who will want to delve into symplectic geometry later, it's pretty fun to work with all these Riemann surfaces. And if you think that you can even plug in gradient trajectories and combine in some imaginative way all this story with differential topology of the manifolds that are involved, right? It gets funny. So that's